All right. So phase kickback. So what happened? I was just looking into some quantum algorithms, and uh, I ran into this term phase kickback at once in one source, and it turned out it's not really explained in any books I have. So I essentially ran some Google search and found some couple of articles and kind of combined all that into one paper, which I didn't share with you yet. It's a small paper. So I think that's helpful to understand how, well, a lot of quantum algorithms work. So this is a list of algorithms that uses quantum phase kickback. I'm sorry, if someone don't understand me, please ask right away. I can repeat or ask questions right away. Don't wait until the end. I don't have a lot of stuff, but I want to go on slowly so everyone would understand. Okay, so let's consider this circuit, this quantum circuit. Let me actually turn all this red thing. Okay, so this is quantum circuit, and I'm not sure if everyone familiar with those, so I'll just talk about this a little bit. So this quantum circuit contains two qubits. This is first qubit, and this is second qubit. And time goes left to right. So we start in this state, and then we apply this gate, and then we do measurement. And A and B, it's not part of the circuit. It's just kind of point of time to talk about this circuit. So at point A in time, we are in state, well, plus psi, or psi, is it psi, psi? Psi, I think. So it's plus psi. And what is plus, actually I explain right here. So plus is also known by name plus x, or 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 this is just equal superposition of 0 and 1. And we can get to this by applying Hadamard gate to state 0. Okay, yes. Yes. So, and U is just arbitrary operator or matrix. It could be anything. So on this diagram or circuit, uh, well, that depends on algorithm. Yes, so the point is it doesn't matter. Any U will do. Any operator. It doesn't matter. They all will. It doesn't matter. It will work regardless of what U does. Okay. So and this black dot is controlled operation. So that means that uh, operator U will be applied to the second qubit only when first qubit is 1 in cat 1. So in a lot of cases this is controlled not, but we don't have to restrict ourselves to control not. That's any controlled operation. So we start at equal superposition here. So at point A, we have equal superposition and psi. And I just multiply by psi just to make it more convenient later on. So is it clear so far? Good. Okay. Yeah. Okay. All right. I'm sorry, Stefan. That's Yeah, I got it. So this is tensor product. Uh, so essentially, it's yeah. So that makes sense to you, right? Yeah, tensor. Yeah. So tensor product is the way we combine two qubits together. So this state on the right, this is combined state for those two qubits. Okay. So I can assume you know something about quantum computing. Like, well, some of us listen to Mike presentations for about a year, so we cover that stuff. But if you need to know, if you have questions like that, please ask. Actually, I'm not sure if it's Scott, if it makes sense to. I'm sorry, not Scott. Yeah, to Scott. Scott, does it make sense to you? Because you didn't go to those, right? Okay. Oh, I'm sorry. Actually, I'm sorry. I think I got. I just clicked a couple of times, and this is just I advance any click advances me here on these slides, on those slides. So I didn't mean to do that. I'm sorry. For right now, it's arbitrary psi, arbitrary u. Okay. So at point in time b, we apply this operator u conditionally when first qubit is 1. First qubit is called control qubit, and second qubit is called target qubit. And this terminology comes from controlled knot in classical state. So controlled knot in classical case works this way. If control qubit is 0, then nothing happens, and both bits just travel to output without any modifications. But if control qubit is 1, then target qubit get flipped to its opposite. So if it was 0, it becomes 1. If it was 1, it becomes 0. Uh, and the control qubit always stays the same in classical case. So that's why we use this terminology, control qubit and target qubit, even though we'll see a little later it's not a very good terminology in quantum case. Okay, so at point in time b, we apply operator u when control qubit is 1. So we apply u to state psi, psi. So does this make sense? Is 1. Yes, yes, black dot exactly means flip on 1. So generally speaking, we can flip on anything. We can flip on 0. I mean, we can create a gate that would flip on 0, or we can flip. Yes. Yes. So generally speaking, we could flip on any function of control bit. It's not very interesting when we have only one control qubit, but we could have actually many control qubits, and we could flip on any function of it. Let's say we can flip, let's say we have 3 control qubits, and we could flip on when control qubit is 101. We can create any function. But but in this particular case, we flip on 1. So everyone clear on that so far? Okay. All right. Now we're going to modify what we do a little bit, and we're going to restrict state psi to only eigenvalues of u. So this is like big restriction, but we just do this to get this phase kickback. So by definition, that means that apply u to state c the same as to multiply this by some constant, some number. So we're going to multiply by e to the I phi. Generally speaking, we can't restrict ourselves to e to the I phi, but in quantum case we can, because probabilities had to add to 1, so we can't really have big coefficients for probability amplitudes. Like probability amplitudes coefficients like here. Here, in this case, they are just 1. I'm sorry, 1 over square root of 2. Like in this case, it's, oops, sorry. It's 1 over square root of 2 for both cat 0 and cat 1. So we can just multiply c by e to the I phi. And e to the I phi, it's earlier, what's called earlier formula. So this is equal to cosine phi plus I sine phi. So any questions so far? Yes. So we have some specific matrix U and specific state psi. That means we have a specific constant that effectively replaces U to operate on this state. Okay. So in point of time A, we have this state. This is just from previous slide, actually. Exactly from previous slide. And in point of time B, on previous slide, we had operator U here. And because this is C is eigenvector of U, we replace U with this constant. Or number, actually, probably not constant, number. So that's the only change so far. Okay, now on previous slide, after U applies to psi, we can not factor out psi anymore. You see psi is factored out here, right? So this is first qubit, and this is second qubit. After we apply U to psi, we cannot factor psi out anymore. Because result of U psi, it's some new vector or state. represented by a vector. So psi cannot be factored out anymore. Yeah, so we cannot like move it outside because you can't leave u here. U applies to a vector. So this u psi is essentially one vector, new vector. Yeah, yeah. So it's gone. I mean, we cannot factor it out like in, yeah, yes. Yeah, new vector or new state. Now, in this case, in eigen vector case, we actually can still factor psi out, which I did right here. Because e to the I phi is just a number, so I can, because, yeah, yeah. So essentially, we can think about it as it's not modified. So I factor this out, and we have, okay, and because I can factor psi out, in a sense, I must factor it out. If I want to separate this combined state of two qubits into two separate qubits, that's the only way to factor, I'm sorry, that's the only way to separate those two states up to a global phase. So we can put like minus sign here if you want. It won't change physical state. But up to global phase, that's the only way to separate those two qubits. Well, actually, not. We don't know that. Not necessarily. They could be entangled, maybe not. I can, maybe, but I'm not sure that's the true in general case. Yes. Well, but what I'm saying here mostly is even if this state is not entangled, so completely separable, it's not separable in a way some new state and then psi. It won't be psi anymore. It would be something else. It would be two new uh, states. Psi will not be one of them. Correct. Yes. So yes. Yeah. Tensor product. Yeah. Yes. Yeah. So because we can factor psi out, that means it's the only way to factor it out. So my point is, this operation did not change target qubit at all. So target qubit is the same as before we did anything. It's the same as before we applied this controlled U operation. Okay, so that's kind of strange because in classical case, control qubit never changes, but target qubit changes. Yes, control qubit, yes, but not the target qubit. Okay, so by the way, it's well, actually, generally speaking, controlled operations in quantum case they're symmetric, and separation to control qubit and target qubit is just a legacy of classical state. So in fact, if you look at this in X, in oh great, all right. I'm sure. I'm not sure if you could see this, but they just told me that there is no 40-minute limit on our session today because it's kind of I didn't pay for. I'm using Zoom.us or Zoom to record this meeting, and I'm not to record, to present this to you, to share my screen, and they just told me it's free for today. There's no 40-minute limit. Okay, so if you look into the control operation from different coordinate system, like from plus x from x axis. So normally all the discussion is in Z basis, which is default basis to talk about quantum computation. It's also called computational basis, but it doesn't mean that the only basis. There are infinite number of bases. For instance, if you talk about our three-dimensional case, there is like 3 dimensions. Like, so we can talk about X dimension or Y dimension, and if we actually discuss controlled operations from X perspective, the controlled and target qubits will be flipped. So second qubit becomes target qubit, and first qubit becomes, I'm sorry, first qubit is target qubit and second qubit is control qubit. So it's actually completely symmetric in quantum case. But what I'm saying that separate the naming convention control qubit and target qubit is just legacy of classical C controlled operations. In quantum case, actually both qubits are completely symmetrical, and we can talk about control qubit or target qubit only because well, yeah, and it's so in some sense it's completely symmetric, but I don't know everything about this. I'm not really ready to explain this to you in full detail anyway. Yeah, no, it's yes, that's correct way to think about this because we are in computational basis, which is Z basis, and this diagram actually explains well, somewhat classical case because we say we flip on one here, but on some diagrams you could see controlled knot operation, Well, also this is controlled not operation, but uh, well, you could on some papers you can see controlled not operation described as two black dots connected to each other. So it would be this black dot and black dot on the bottom, and they will be connected. And that means controlled not. This is not the standard notation, but it's used in some places. And that kind of tells that actually this is exactly fully, C naught is exactly fully symmetric. It is. But maybe actually, yeah, I may be confusing some things. I didn't investigate this much. I mean, a lot about this. So I can look at this later on, and maybe we can talk some other time about this. So I'm not positive about this. What my point is, there should be surprise about this control and target qubit being kind of exchanging their roles, because controlled operations, they're not like all that asymmetric. Mhm. Yes, I don't. Okay. So any questions on this slide? Okay. So nobody. Maybe someone. If someone talking, you're on mute. Okay. So this phenomenon is called phase kickback. That's so phase. So what's being kicked is actually eigenvalue e to the I phi. I to the I phi is eigenvalue of psi, and it's being kicked to the target qubit. So phase of the target qubit get changed by this, modified by this eigenvalue. So that's the phase kickback. Okay. Yes, the control qubit changes its phase, yeah. And the target qubit remains the same. And this turned out to be very useful in those algorithms. Or at least in those. Okay, so now I started to think what are actually requirements for phase kickback to occur. I did not find this anywhere, so I kind of came up with those three requirements. If you find those are wrong, please let me know, because I want to know about those. So first requirement is the control qubit or qubits must be in some superposition. So in my case, I chose plus, so which is equal superposition. So you cannot just do like it, just put one here, because what's going to happen if we apply controlled U operation to this state? Well, we apply U to this state, and because we restrict ourselves to psi being eigen vectors of U, that means this is just a number. And in this case, number is just a global phase. And this it could be dropped. So essentially, from physical perspective, we get exactly the same state as we started with. There is physically no difference. So we didn't do anything. And if you put 0 here, well, that nothing will change anyway, because control qubit doesn't act on 0. Okay, so that means we have to, control qubit must be in some superposition. I don't think there has to be equal superposition, but I think in all algorithms it's actually equal superposition, because there is no point to have unequal superposition. So any questions about that? Well, actually, yeah, that's a good point. Actually, well, it doesn't matter. In quantum cases, I think all the eigenvalues I ever seen were +1 and -1. And it makes sense to use -1 because using +1 makes no difference because we multiply by this number. So I only use -1. But technically, it could be any other now, anything else but one. If you're you, okay, okay. Well, yes, that would work. And so in this case, well, the e to the I phi, I think it has magnitude of 1. Oh, could we drop it? Uh, well, I think magnitude of this is going to be always 1 because we have this 1 and psi. So those two are valid physically implementable vectors, right? States. If we multiply them by some not a 1 or some number, some complex number with magnitude which is not 1, I, so it has to be 1 because otherwise we would create invalid state. Yeah. So that's the reason to have not some arbitrary number, but e to the I phi here, actually. Okay, I'm not sure that's actually correct notation. I use this, oops, sorry, equal with this tilde or something. That may be incorrect, but I use it anyway. Okay, so this is first requirement. So second requirement is C must be eigenvector of U. We talked about this already, right? So, and third one is, well, U must be applied in a controlled way. The only alternative to controlled way is always apply it. And if you always apply U in this restricted case when C is eigenvector of U, all we do is modify a global phase, and that's again makes no physical difference. And again, we do not make any modification to the initial state. So any questions about that? I cannot see everyone at the same time, but yeah, it doesn't show me everyone at the same time, so I cannot see everyone nodding. Okay, so I came up with those three requirements. So superposition, eigen vector, and control operation. So this has to be controlled. Qubits has to be in some superposition. This has to be controlled, and has to be eigenvector of U. Eigenvector of U, by the way, not controlled U. It doesn't even make sense to be eigenvector of control U because this is one qubit, and this is controlled U is 2-qubit operation. So just little note that phi is eigenvector of U. Okay, so I never kind of talked about this, but psi can actually be many qubits as well. And that does not change anything, I believe, even though I didn't look much into this, because I think our formulas are going to be actually exactly the same regardless. You can just think about this psi as some multi-qubit state. So it's multi-qubit state here, and we just multiply this by some constant, some number, and it kicks back just the same. So no changes here, actually. So we can have multiple target qubits and multiple control qubits and multiple target qubits. That works just fine. Okay, so I'm ready to move to my example. If no one has any questions, I'm going to move to this. Okay, so example I'm using here is actually based on those lectures. And actually, by the way, those lectures are great. And well, this paper is great. I didn't listen to the lectures. It's John Waterhouse. He mostly talks about algorithms. His part about, he just has this overview in the first lecture, and then he starts talking about, well, algorithms almost right away. And I think he actually explained things pretty clearly. I like those better than any other book. In lecture 5, mentions something or talks about something called simple search algorithm. And that's the example I used. Okay, so the problem here is this is a function f. Function f takes two inputs, 2 qubits, and it outputs 1 qubit, or bit maybe. So there are many functions like that, 16 I guess, but we restrict ourselves to have only those 4 functions. That's like artificial constraint. Whoever creates this function for us, like Alice creates this function for us, doesn't tell us which function it is, but she promises that it will be one of those 4 functions. And notice how those 4 functions return 1 only in one case. So this function outputs 1 for input 0, 0. This one outputs 1 for 0, 1, and this one for 1, 0, and this one for 1, 1. So only one, it always returns just exactly 1, 1, single one, and 0 for everything else. Okay, now let's consider this quantum circuit, and this quantum circuit is going to solve our problem. And the problem is actually to determine which of the 4 functions is given to us. So let's say Alice makes this UF, and we'll talk about this, how to make this one. So she makes this for us and just hand it to us, this quantum circuit, and we are not allowed to look inside. All we can do, we can run this circuit and see what it outputs. So when she constructs this U, and we'll talk about how she does it on the next slide, she kind of arbitrarily chooses F, one of those 4 Fs, and creates this UF and gives it to Bob, and he kind of builds this circuit around it. And as a result of those 2 measurements, Bob will get this index. He will get either 0, 0, 0, 1, 1, 0, or 1, 1. And this will be index of this function. So without looking into this function, just by looking at what this function returns, we can figure out, Bob can figure out which function it is. Or in other terms, we will run this function f, which we don't know much about. We don't know which one of those 4 it is. And we will figure out on which input this function returns 1. So let's say Alice gave Bob this function, and Bob ran this algorithm, and he gets 0, 1. That means that function Alice gave to him returns, returns 1 on 1, 0. So those 2 are identical ways to look at this problem. And you can notice this index 1, 0 is the same as this one. So those functions are named by the input which returns 1. Okay, any questions about that? Everyone good? Okay. Okay, so Alice gives Bob this circuit U, and let's talk about this circuit first, and then we'll move to how to build UF. So this circuit has 2 control qubits, which are in plus state, and target qubit is, well, in minus state. And minus state is, well, this one on the bottom is also equal superposition, but it has minus sign here. and it can be prepared by applying Hadamard to 1. Okay, and well, Alice gives Bob this UF, and then after we apply UF, we apply some other matrix which I called M. We're not going to talk about this because it doesn't really matter for our purposes today, but it's just one matrix, and it's a very simple matrix, and it will do something which in combination with this measurement will return 0, 0, 0, 1, 1, 0, 1, 1. And that will give answer to our question. So everyone good so far? So this is hard-coded matrix. It's always the same. But UF is given to us by Alice, given to Bob by Alice. And so the target qubit is just ignored. Well, it won't change, by the way. It will be just minus, cat minus. Okay, now I'm going to move to the next slide. And so Alice prepares this UF for us this way. And this is very common pattern in quantum algorithms, and Mike talked about this about a year ago. So this is a controlled operation, and I do not use the black dot in this case because it could be actually, it's not actually controlled by 1 necessarily. It's controlled by function f, so that's why I could not put this black dot here. It's controlled, so A and B are control qubits, and C is target qubit. And in classical case, for control qubits, just this UF outputs A and B is the same way, it doesn't change them. And the target qubit flips depending on value of function f. And function f is the function we just talked about. So the way this works, actually this is controlled by function f, not operation. It's always not. It's similar to control not, but it's not controlled by 1. It's controlled by function f, not. And if f is, so this is because if f is 0, this 0 XOR C is the same as C. And if function f is 1, then 1 XOR C is not C. It reverses C. If it's 0, it's 1. If it's 1, it's 0. In classical case. So does it make sense so far? Okay. So this is just controlled by function f, not gate. Okay. Now, so Alice prepares this gate. So by the way, we have all the conditions for phase kickback. Control qubits are in superposition. We have some controlled operation. And the target qubit is an eigen vector of our U operation, which is not. We are doing controlled not operation, and minus is an eigenvalue, eigenstate, eigenvector of not. And in case you don't remember any of this, this is Mike notes, And on page 30, you can see that. So this is, hopefully you can still see my red cursor or not. I'm sure, do you still see my red cursor? Okay, so anyway, sigma x is the not operator, and eigen vectors are plus x and minus x. Okay. So we do have all the three conditions for phase kickback, and that's why it's going to work. Now, in the point of time A, we have state A, plus, plus, minus, those. And plus is equal superposition, and minus, because the target qubit is not going to change anyway, I just kept it as a minus, and I kind of spelled out plus as this. So this is plus plus equal superposition of those four states. And you can get this if you get a tensor product of this. This is this state tensored with itself. Okay, and we can rewrite this a little bit. I just move this minus sign over there. So any questions so far? Good? Okay. Okay. So at point B, we're going to consider an example when function f is happen to be f00, which returns 1 on input 00. So we are going to apply matrix U f00 on 00 and do nothing on in every other case. So this is how it works in classical case, and it will automatically work in any other state. So it will work in superposition or for any other state. I mean the circuit in general. Okay, and now because our target qubit is eigenvector of u with eigenvalue -1, we can replace u with -1, and the rest is the same. And I just rewrote this a little bit. I factored out minus because it didn't change, because I can do it. So this is a fully separable state, which is, in other terms, fully non-entangled. The only change is here this minus sign. This is the result of kickback. The eigenvalue -1 got kicked into the target qubits. 2 qubits in this case. Yes. It's not. This function f. Function f takes 2 inputs, but we construct u, Alice constructs u for Bob in such a way. So function f, takes those 2 arguments, and we just need C for the circuit to work. Well, because okay, so the circuit UF, it has to be unitary, right? Which means if we apply 2 times, it will return us the original state. So it has to be unitary. If we just build a matrix out of F, it won't be unitary in general case. So that's why we need to do this. Also, we want to have we need phase kickback to happen. So that's why we build it this way, UF. So any questions about that? Everyone good? Okay, so and this is just second slide, and this is exactly the same, but it happened that Alice prepared function 0, 1 for us, and result of that, we apply UF to state 0, 1, and the result is we multiply phase of 0, 1 by eigenvalue of minus, which is -1. And that works exactly the same for F10 and F11. We just get minus sign in different places. So matrix M in combination with two those measurements, allows us to convert this change in phase, this negative phase, into a classical result 0, 0, 0, 1, 1, 0, and 1, 1, which we're not going to discuss how this happens, but because, well, it has nothing to do with phase kickback. So that's all I had for today. So yes, I'll send you a link, and this is Google presentation. I can share this with everyone. I'll just make it, yeah. So I have, yeah. Well, I'm not sure if you actually want slides because I actually wrote a paper about this, which has everything. So it has everything, maybe even more, and I have some references. So the best resource I've seen about phase kickback is actually this Quora article. This guy actually explained this, but he didn't talk about requirements. He didn't say like what you actually need, and actually spelled out things a little better than he did. But this is a very good explanation, I think. The only thing I don't really understand why he has those 2 pi here. I assume he kind of treats this phi differently. But in most places, I didn't see this 2 pi in many places in quantum case. So I think you can just ignore and pretend 2 pi is not here. Okay, now I have this second article, which, yeah, also linked. Yeah. Okay. So, yeah. And this second article, which is good article to read like after the first one, it has some more detail. They actually talk about some other things like uh, So you can read it. I actually don't even remember what else he talks about. And this is those lectures I talked about. I think they're great lectures. And when I get frustrated with reading some other books, I read this one. And it kind of makes sense after I read this one. I'm not sure if that's a good book to read first. Uh, okay, and Mike notes, I didn't link to those because they formally don't talk about face kickback. But Mike actually does talk about something similar. I think here, those are extended notes. And yeah, so this is pretty good. This is very close to face kickback, except there's no talk about when it happens. But essentially, this is face kickback. Yeah. Yes, that's exactly my point. That's the main point. I was wondering when it happens. Nobody explained this. Yeah. So as soon as I figure out how to publish this paper somewhere, which I think Mike published this on GitHub pages. That's where he Well, I am kind of halfway through figuring out how to do this on my own. So I want to know how to do this. But I'll send email after that to all participants I know about anyway. To Denver uh, to Denver group, and I don't know emails with other guys. But oh, Aaron, okay, great. Oh, okay, great. So I'll send email later on. Hopefully today with all those links, so you can take a look. And if you have any problems like typos or you want to correct my bad English, which I know is bad, so please do. All right. So that's all I had for today. So I'm gonna stop recording. You're welcome.